Okay, when current carrying conductor placed in magnetic field, then it will experience force, and that force is equal to I L B sin theta, where theta is the angle between L and B. Now we have to calculate the torque on the current carrying coil when it is placed in external magnetic field. So this is the magnetic field, direction of magnetic field, strength is B here, and here is a rectangular coil in which I current is flowing here. I. We write here capital I. Okay. So first of all, we calculate the force on PQ, again force on QR, again force on RS and SP. So force on PQ, force on this conductor QR, force on RS, force on SP. So PQ is perpendicular to magnetic field, so force is I L B sin theta, but theta is 90, then sin theta is sin 90 is 1, so we write only I L B. Direction of force, so this is the direction of magnetic field and this is the direction of current in upward direction, so force will be we can see here direction of magnetic field, direction of current, so force will be in inward direction. So this is inward direction. Okay, force on RS, RS is this, so this is the magnetic field and this is the sorry, right here for inward, this is cross. Okay, this is for inward. Okay, for RS, this is the magnetic field, current, and this is outward direction. Then force is I L, for here we write L, so small l, I L B. Again theta is 90, then sin theta is 1, and this is in outward direction. This is in outward direction, so we write here outward. Now force on QR. So here the length is W and the angle between B magnetic field and length is alpha. So this is I W B sin alpha. By applying left hand rule, the direction of force on QR is in inward direction. Similarly, force on SP, so this is again alpha, then this is IWB sin alpha, but force is on this conductor is in upward direction. On this is downward and this is outward. This is inward and this is outward, so we write here this. So these two forces are experienced on a current carrying coil. We see that force on QR is equal to force on SP and are opposite in direction. Then these two forces are cancel each other. So force on QR, this, and force on SP are cancel each other. So we remove this. Okay. Now force on this conductor is in inward direction, force on this conductor is in outward direction, and point of application of force are different. Whenever here is an object, two equal and opposite forces, that means force on this point is in this direction, force on this point in this direction. Whenever on a single object there are two forces act on a different point in opposite in direction and magnitude is equal, then what will happen? It will rotate like this. It means there is a torque. So it means this current carrying conductor, current carrying coil experience a torque. So for the calculation of torque, we write here tau is equal to force, and that force is ILB into perpendicular distance between two forces that we call R. So simply we write tau is equal to F cross R. For the calculation of R, this is the force and this is the force, we have to calculate this. So we can draw here one thing is more, that this is the direction of magnetic field and this is the direction of area vector. So this is angle is theta. Now draw a side view, top view of this figure, that is Q R as the magnetic field, okay, the magnetic field, and this is W basically, and this is alpha as this, and this is the direction of area vector. This angle is theta. We write here as T, okay. So one force is here in outward direction, one force is here in inward direction. So we have to calculate this distance, perpendicular distance between two forces. So we have to calculate QT. If this angle is theta and this is perpendicular to W and this is perpendicular to, this is the perpendicular to this magnetic field, then this angle is equal to theta. Then we can write here from triangle QRT that sin theta is equal to QT upon hypotenuse QR, then QT is equal to QR sin theta, and QR is width, this length, so QT is equal to W sin theta. Okay, so formula for torque is F into R. This is basically tau is equal to force into QT, and QT is W sin theta. Then this is force is ILB into W sin theta, and this tau is equal to I B L into W sin theta, and L into W is the area of this coil. This is the length and the width, so L into W is the area. So tau is equal to I B A for area and sin theta. So torque is equal to I A B sin theta. Okay. So now when torque is maximum and when torque is minimum, so we know in case of sine, minimum value of sine is 0. So now let if here theta is the angle between A and B, that is between the magnetic field and area vector. So now let if theta is equal to 0 degree, then torque is equal to 0. What does it mean? That when area vector is perpendicular to, parallel to, when area vector is parallel to magnetic field. So we write here N S, and this is the coil, and this is the area vector. Okay. So now if we coil rotate in such a way that it will move like this. This is the coil now. This is the direction of magnetic field this is the direction of magnetic field, and this is the coil. So this is the area vector. So area vector and magnetic field both are in same direction, and angle is 0 and torque is minimum, torque is 0. It means when the current carrying coil placed in such a way that area vector and magnetic field is in same direction, then torque on this coil is 0. So this will like this. This is the area vector and this is the direction of B. So for this, torque is equal to minimum. Okay. Next, now if theta is equal to 90 degree, second 90 degree, then torque is equal to I A B, and this is minimum and this is maximum. So when the angle between A, area vector, and magnetic field is 90 degree, then torque experienced on current carrying coil is maximum. So this is N, S, this is the direction of magnetic field, and this is the coil. This is the coil, and it will be placed like here, like this. So area vector is in outward direction, this z-axis, and this is the direction of B. So this vector A, area vector, and B is at 90 degree, and when this is at 90 degree, then torque is maximum. So this is the A, and A and B are perpendicular to each other. So that's all about the torque experienced on current carrying coil.